quiz today, wasn't it? I always wonder because maybe I don't know something that's going on. Anyway, questions about anything I assigned? I put some of the solutions down. What I actually was use Claude to actually get the solutions on some of this stuff. If I start writing this stuff out, my handwriting is not exactly stellar. It'll make it difficult to understand. Some of it I did myself and put on there. One thing I did want to say, I haven't used it in a bit. Have you seen those posts that have like a graph paper kind of thing where I have the solutions? You remember those things? That's called MathCAD. Now I'm going to just, as a personal, well, as something I'm telling you, if I was sitting where you were, I would want to know this. I have no interest, I have no stake in MathCAD at all, but when I was at NASA in 1988, a guy who was a scientist up there, he showed me MathCAD. And the reason he used MathCAD was it was what you see is what you get. Basically, it had a way to graphically, if you wanted the integration of I of t dt, it would show you the integral sign, all this stuff, and you could do any kind of complicated integrals, any stuff like that that you do on MATLAB. The thing about MathCAD is it will instantly update. If I change any value up top, instantly everything else has changed. And it is not nearly as powerful as MATLAB for large problem sets and everything like this, but most of the stuff, I can't think of anything that doesn't do better for undergraduate and a lot of graduate material, and I use it extensively. For these problems that we're doing, I can solve them that fast on MathCAD. If you know, with a lot of it, you have a lot of little things that you have to get right and you have to change things, especially with convolution, MathCAD. You know. So I said that, and now I'm going to get into the problems. We did this section 3-4 problems, didn't we? All of them? Yeah. Those problems are very important, but 3-5 are the ones I think that are more challenging. That's my opinion. And this is where we have two random variables that are not correlated together, or I should say that are independent random variables. And you're going to have a third random variable like z is equal to x plus y, or z is equal to x minus y, or something like that. And these things can get a little tough. Now, we'll show you a trick too. So, can you read? I'm going to go back and do some other ones. So I'm going to start at 3-5.5. You have it there? How many tried these again? Did you do them all? Did you have any problems with them? You did them all. Good for you. But those are difficult. There's some in there that we're going to spend time with because on this next quiz and on the final, this is a class of problems that give people real trouble. Come on. Come on for 1 second. How many tried 3-5? 3-5.5. This is actually an easy one. I'll show you a trick. So they give us two variables, and they say they're independent, x and y. Then it says that let z equal to x plus y. If I'm wrong on anything, just let me know. And then it gives you f of x as, is it 2e to the minus 2x u of x?
That's for y.
Oh, that's one? Sorry. You're going to see it won't even matter, but I'll make this f of y then. And then f of x is equal to, is it 5e to the minus 5x u of x. And then you get this right here. Now that means that z itself, if you look at this, you get an equation for y. And if you want me to actually prove this Anybody wants it, just tell me. But at the end of the day, because there's a plus sign here, you get f of z equal to f of x, and the symbol will be convolution, f of y. You all see that there? Everybody with me on this one? Okay. Now, next. You're used to seeing convolution written a little bit differently. And I'm going to bring it back to what you're used to seeing for a reason. We're going to do a Laplace transform of this. And it'll be much easier to solve this. Typically it is, at least. So if you think of this, if you have, now z is just, it's a variable right here. But if you have f of z of t, think about this, could be equal to f of x of t convolved with f of y of t. Do you all remember that in convolution they usually use t? This is the same principle. Z is a dummy variable. These x and y's are going to get integrated out. Follow me on this, class? Everybody with me on this? So if you take a look at this, we're going to note that t is going to be as z is at the end of the day, but I want to show you this way. So if you have anything f of z of t, and you have these two functions as a convolution, you find which of the functions has the most going on, you don't do the flip and shift. I'm just going to say it's f of x, doesn't matter in this case. So I'm going to say f of x of tau. Then the other one you flip first, so you're going to get f of y of minus t. Do you all remember that? And then you're going to add tau to it. Follow me? So you're going to get times f of y of t minus tau d tau. And technically it's from minus infinity to infinity. That's the definition of convolution that you saw in signals and systems. It was a lot more, it's probably a lot more familiar to you. Everybody remember this, right? Now if you do this, and you're doing convolution, I'm going to go ahead and put, doesn't matter which one I do, I'm going to take this one, I'll take this, f of x, and I'm going to be, this is going to be something that I don't flip and shift, and I'm going to use tau as the variable, because that's going to get integrated out anyway. So I take tau here, and this is going to be my f of x of tau, and that one is just going to be start at 5, and it's going to decay down. So it's going to be 5 e to the minus 5 tau, u of tau. And I'll put the u of tau there, but it's not necessary for when I'm drawing it. Everybody agree with that? I'm doing it this way, trying to do it in the steps that you were probably taught. If you had signals and systems, this is the way most of the time they show you how to do convolution. The next step down here is I flip the next function. So right here, I'm going to have f of fy of minus tau, and that looks like this. And that's going to be e to the plus, not minus, and it would be 2 plus, and it's going to be 2y. And then it would be u of minus tau, or I mean not y, tau. Do you all agree with that? I want to make sure everybody sees this, right? Then you add the t inside that argument. Inside the argument right here, the f of minus tau, f of y of minus tau. Now you add the minus t. Follow me, class? When you do, it does this. I'm going to just alter this one. Now it'll do this. It'll come, it won't stop there. It'll go here. And this equation right here is going to be 2e to the minus, and then it's going to be 2 times t minus tau. And it stops times at u of tau. So right here, this is the variable t. Do you all follow me? I'm going to change out t to z at the end, but you all follow me on this. Now, this is the old thing where you take the functions, flip and then shift, and then you drag this curtain this way, if you remember. And you look at the overlapped area and do the integration. Y'all remember this class? All right, so if you look at this, the overlapped area is right here, right? Agreed, class? So what I need to do is multiply this function point by point with this function and then do the integration to get this value. First, you got to all agree with me, right? And if you look at this, now, both of these, the extent is infinite, isn't it, on both of them? Okay, so if you do this, when I look at my f of z of t right here, I'm going to put it up here, or my f, I'll call it z of capital T. What that is going to be is the integration, and here I'm going to have 5 times 2 or 10. I'll take that in front. All the integrals start, as far as tau goes, at 0, and they end at t, which will become z, but I'm doing it for a reason this way. And now I have to take this, e to the minus 5 tau, times this, which is going to be e to the plus 2 tau times e to the minus 2t d tau. I'm just writing this down for completeness. This should look very familiar. This is a classic problem, 2 exponentials. Everybody with me on this one? I don't know if you may have just used the symbols they use, but in this is for me personally, I'd rather use the t there because most people are familiar with using convolution time, not spatial convolution. Spatial convolution we use all the time, but it's usually higher level courses. So then I get f z of t, which will become z, is equal to 10. And then I can take out the e to the minus 2t here, right? Because it's not a function of tau, correct, class? Then I integrate this, and I have an integral from 0 to t of e to the minus 3 tau d tau. And I'm doing nothing tricky here, and I'm just going to execute that integration. And that's going to be 10 e to the minus 2t. And then when I do this, I get minus 1/3 e to the minus 3 tau evaluated from 0 to 1. Here, I'm just pushing the numbers here. And that means I have 10/3 e to the minus 2t here. And then when I'm done with this, I'm going to have 1. And it's going to be minus e, so this should be t right here, e to the minus 3t. And I don't know if the answer is in that form. You can multiply this through and you're going to get e to the minus 2t minus e to the minus 5t. Do y'all follow me, class? Now I'm going to convert to z. I'm going to put t and I'm going to replace it with z. You good with this, everyone? And I'm going to do it right. I'll do it right here. And I'll put my f of z now is equal to 10/3, pardon me, and then it's going to be e to the minus, I'm going to do it this way, e to the minus 2z, 1 minus e to the minus 3z, and then it's going to be times u of z, so it's only for z positive. I'm going to ask something. I think that's right. Is that right? Or did he have it as e to the minus 2z minus e to the minus 5z? I don't remember, honestly. Anybody? Y'all, who did this problem? You did it, right? Did they have that form or which?
My calculator did it slightly different.
Okay. What's that?
It was in a slightly different form.
It's basically, do y'all follow me on this one, class? Now, if I ask you to sketch it, please be attentive here. If I ask you to sketch this, you always start at the extreme points, at z equals 0, everything below that 0, right? Then you take it at z goes to infinity, and there's one more factor that we worry about. So if you look at this, if you sketch the density function, f of z, at 0, what is it? Well, just go here. What is e to the minus 0? What is 1 minus 1? It's 0, right? It starts at 0. So we know it starts there. What is it at z goes to infinity? What is e to the minus 2 times infinity? 0, right? E to the minus infinity is 0. Do you all agree with that, class? So it's 0. But somewhere here it's going to have a max. Do you agree with that? Well, how would you find a max? I'm going to ask a really dumb question.
Yeah.
Absolutely. You take the derivative of this and set it equal to 0, right? And solve for the value of z. Do you all agree with this? So you could find the maximum value, which is the most likely value of z, right? You got me on this? Now, what else did he ask before I say more?
fz at 0.
Well,
the
that's
value,
it.
value for which fz of z is greater than 1. And then
What,
probably
say it again?
the value for which fz of z is greater than 1.
Oh, okay, how do you do that part? Well, you find it where fz of z is equal to 1, correct, class? And set it equal to 1 and then solve for z, right? Now, your calculator should do that in a heartbeat, but how would you solve it? I mean, I don't know how it's supposed to do it. Because I don't remember looking, I don't remember that part. But what would you do? If you set this equal to 1, what would you have to do? Well, you're going to have what? If you set it equal to 1 here, you really have two exponentials with different coefficients, correct, class? I mean, if you multiply it through. So that's an iterative solution, I believe, isn't it? It's one of those transcendentals. I don't think there's a closed form. Is there a closed form did he have on that one? Did you do your calculator do that one, or?
Yeah, it was a range between two different numbers.
Yeah, well, what you need to do is you say f of z equals 1, and if it's 1, that's equal to, I didn't do this part, but 10/3, and then you're going to have e to the minus 2z minus e to the minus 5z right here. And that means 3/10 is equal to this. I'll just show you how you can do it. E to the minus 2z minus e to the minus 5z. Can't do the log stuff. For this one, if I take the log on this side, minus 2z, or minus 2z, take the log of this. I can probably fuss around with it and get it an approximate value, but can anybody look at his solutions, not the ones I posted on OneNote, and tell me, did he do that? Just, he probably used a solver for that one. Did you do this one?
No, but where are his solutions?
Huh?
Where are his solutions?
In the beginning of the class, I put down the PDF of the book, and I have a PDF of the solutions manual. Then I also posted, did I post the solution for this one or not?
You did.
Okay, I will. But I'm about to show you something. I don't. You all know how to, I mean, you would know how to get that with your calculator by a solver method, right? Anything? It's hard to read his writing, the solution manual's writing. No? I'm not really worried about that, but I have one more point. Is there another, what does he ask besides that? The f of z between a range, it's going to be from here to here, but some minimum, some maximum, but this right here is based on solving for this. And you're gonna get two solutions for Z, and I frankly don't wanna spend too much time on that part.
The next part is the probability that z is greater than 0.1.
That Z is greater than 0.1? So how would you do that, basically? I'll take it from anybody. We have f of z, right? What's the probability of z being greater than 1? It would be the equal integral from 0.1 to infinity of f z of z, bz. Do you remember this class? It's that straightforward. We've got, it's really going to be 10/3, right? And if you look at this, the first integration is e to the minus 2z from 0.1 to infinity, so that's going to be e to the minus 0.2 minus e to the minus 0.5. I think that should be right. Do you agree, class? Can you give me that answer, by the way, just so I can put it up?
0.9602.
Is that what he has? Or what I have? Is that the right answer?
0.602.
Could you see his solutions or not?
Yeah, I just pulled it up, but I'm not sure exactly what he's writing for the.
Get expanded. It's hard for me to read his writing because I have to blow up. But I think, now I believe his answer on this one's right. It could be, there's some wrong answers, but,
That's what, yeah.
that's what it is.
all right. Do y'all follow me on this one? Now, here's the trick that I like. And you will too, with certain, well, maybe you won't, because your calculators are pretty powerful, but convolution oftentimes is terribly irritating. Does yours calculator do convolution or not? You have to set up the integration, correct, class? Here's the trick that I wanted, the reason I'm spending time on this. I'm going to erase this. And I'm going to remind you of something. First, both of these functions, the f of x and f of y, the original ones, are only valid for either x or y greater than 0. Everything else below that is 0. With me? So you can use the Laplace transform method. But instead of z, we're going to use t because you're familiar with t. So if you think about this, I know that f of t will transform into f of s. Everybody should be familiar with that, right? And you have transform pairs that you're probably very familiar with as electrical and computer engineers, especially in your upper level classes and communications. I guess it's a junior elective. In a lot of the senior electives, Laplace transforms are very important. Did you have controls yet? Have you had, all right, well, you had signals and systems. In control, you had controls?
Yes, sir.
You know that Laplace transforms make up a large share of the actual way you do analysis. You can find out a lot of information about stability. You can do all sorts of analysis and bring feedback loops in. That's in the continuous time domain. Just a little preview of where you're going. In the discrete time domain, which is just about everywhere nowadays, it's all sampled and quantized. It's the Z transforms, which are extremely powerful and used everywhere these days. But sticking with the Laplace transform, the reason I brought this whole thing up is we have two functions. We have, the first function is 2e to the minus 2t u of t, and that's convolved with the second function, 5e to the minus 5t u of t. Now I'm putting t in here because you're familiar with it. I could put x and y, but somehow that will confuse the issue. Now you're familiar with that, right? What convolution in the time domain is what in the S or frequency domain? Anyone?
Is it? Yeah, was it multiplication?
Yeah, it's multiplication, the two functions. If you don't recall it right off the bat, remember if you had x of t convolved with h of t, you actually get x of s times h of s, right? And then if you've got this, you can do partial fraction expansion and take it back over here and get the time domain form. Do you all remember this? How many do? I'm curious. All right, you're gonna use this a lot, guys, and I kid you not, at least in the upper level classes that I'm familiar with, and I can speak for my own radar and EMC and probably microwave, I'm sure microwave, and almost all the courses, let's see, if you get anything with information theory or digital signal, let's see, imaging and digital signal processing, all that is going to be based heavily, starts with Laplace, goes to Z. So remember what I'm telling you, it's going to be used all the time, typically. So this right here, when you do convolution of two functions, you know what you're effectively going to do. Take the transform of this and put it in the frequency domain. Do you remember what the transform of, I hope you do. If you have e to the minus at u of t, and you wanted the transform of that, do you remember what it is?
1 over S.
A plus s. Do y'all remember? Do y'all remember that? It's one, please remember it. It'll save you work. I'm speaking from my heart here. You don't have any idea how much trouble it can be convolving crazy functions. But you should probably know that. And I can be very, well, I'll just make it real clear. So I'm going to take this one and do the transform of that. That's 2 over s plus 2. And it's multiplied by 5 over s plus 5. I'm showing you that this is something that should make sense to you. Do y'all follow me on this? Here's the two functions. These are the transforms of the functions straight away. What's the next step we always do? Well, it's a pole zero expansion, mathematically stated. But what you're going to do is, you see you have only two simple poles, right? You don't have double poles. You don't have an S on top. So you can expand this and say it's just going to be A over S plus 2 plus B over S plus 5. I hope this is making sense. I'm doing it this way so I don't have to cover the characteristic function, because the characteristic function, I don't know why they did it this way, but it uses effectively the negative Fourier transform, which really ruins all the tables you have. So I'm doing this and just showing you that this is, Laplace is better. Okay, stay down. Getting down to that point, how do we find A? Gonna ask for 20 points, play a game. How would you get A? It's called the cover-up method. You all remember that? What do? You see the pole here is at s equals minus 2, correct? So you multiply everything by s plus 2, gets rid of that. It's multiplied by s plus 2 here, and the s plus 2 here gets covered up. With me? And then you evaluate everything at s equals minus 2. This s plus 2 goes away. The s minus 2 here will become 0, gets rid of that term, and that means A becomes what? That evaluated s equals minus 2. Can you take a look at that? What is that going to be? It's 10 over 3, right? So this is 10/3. How many know what B is from your old signal state?
Negative 10 over 3.
It'll be exactly the negative of that. They're simple poles. Whenever you expand simple poles, if that's plus 10/3, this is minus 10/3. Everybody with me? And if you don't believe me, go ahead. Multiply everything times s plus 5 and evaluate the remainder at s equals minus 5. Well, that goes away. That goes away. And at minus 5, what is it? 10 over minus 3. See that? It's going to be minus 10/3. So this becomes minus 10/3. Then go ahead and take the inverse transform of that. Now, if you look here, here's the key. We have poles, 1 over s plus a, right? That means we're going to have functions e to the minus at u of t, and they're going to be scaled by whatever that coefficient is, a or b. So when you go back to the time domain on this means my f z of t simply becomes 10/3 e to the minus 2z u of z. And then it's going to be minus 10 thirds e to the minus 5z u of z. And that will be my fz of z. But I did this in the time domain because I wanted to make sure at least I tried to relate it to what you had before. Do you all remember that? All right, here's the question. A little bit more involved. You're probably a little rusty with your transform pairs. All right, that one you should know. I'm just telling you, right now, if I was you, I'd know that you don't have to know this to do the problems, but I prefer doing it that way to convolution. Now, if you want to convolve the crap out of stuff, have at it. You know, it's not for me. I like the short route. I like transforms if I can use them. But you can't always use transforms. Now, what if I have this? Just listen. And I've got this right here. I'm going to be careful about that. What if one of these, well, I better not say too much, but I'm going to ask this part of it. If I asked for the mean value of z, how would you get it? The last part, then I'm going to move on. Well, you can't use Laplace on this one, so don't go down that route. I'm going to multiply z times this, right? So it's really going to be of the form z times e to the minus az integration dz. That is an integration by parts, but I think your calculators can do those things fairly quickly, can't they? You can get that fairly quickly. I think I covered all my bases on what I wanted to say, but I did want to bring that up because that way we don't have to use the characteristic function. And I doubt if anybody did it that way, but that is a neat, it solves a lot of problems. Okay, that's what I wanted to say about that problem. And I hope that helped you. How many tried this problem before? Did you? He did it. Anybody else do it or take a look at it? Convolution is something that gives people trouble. I'm telling you, it gives them a lot of trouble. This stuff makes life easy for me. Okay, next problem. Well, we can do the first one. I think we can go through it fairly quickly after that little discussion. And I bet you guys just nail it in the heartbeat. How many tried it again? First problem. Okay, at least try it. Let's see if we can go through it quickly. Could you give that? You can look at it right
Yeah, which one? 351.
there. Yeah.
Random variable x is a properly density function of f of x. Fx of x is equal to 2x between 0 and 1 and 0 elsewhere. An independent random variable y is uniformly distributed between -1 and 1.
So Fy of y is equal to 1/2, and it's between -1 and 1, right? Go ahead. And they want what? The dense is z equal x plus y or what?
Z is equal to x plus 2y.
Okay, this is a good problem, and I'll tell you why. This is just a slightly different problem than you're used to. I'm going to say this much. Statements like this, if you aren't familiar with what you're doing, you just, crammed the night before, they'll throw you. You're used to x plus y, not x plus 2y. Follow me? A lot of ways to do this. Probably the easiest is if we had a function z is equal to x, call it x plus, I don't know, x plus u, then we knew that f of z is equal to convolution of f of x convolved with f of u of u. You all with me? If in fact we had a function that was just like a constant, not a constant, but a linear function. Not 2x, but just x. Follow me? Something equivalent. So what we do is take this density function right here, and I think he does it this way. Now there are tricks to this too. There's a lot of tricks to this. But if you take a look at that density function right there, I can make a new variable, and I'm using u. I don't know what he does. I can say f of u, and I'll start by saying u is equal to 2x, right? Because I don't want a 2. That's my whole goal. That's the reason I'm creating this new function. With this, I forgot, does he do that or does he do it a different way? It doesn't matter. There's a couple different ways to do this. In my opinion, this is the easiest. You all see this? Because we want to match this pattern. We want something that's just x plus y. We don't want x plus 2y or x plus 3y or x minus 2y. You all follow me on this, class? We want this form. So if u is equal to 2x and x has a span from 0 to 1, this has a span from 0 greater than u less than 2. Follow me? It'll be twice as wide in terms of its actual range. Twice the range. Do you all follow me? But the density function on this is going to be what? If you think about it, this, if the density function for x was 2x, this is simply going to be u, and it would be valid, f of u would be valid from 0 to 2. And if you look at that in fact, just take a look at this. F of u 1, 2, here, sorry. I think I did that one. This is not right. Give me 1 second. There it is. It's u over 2, pardon me. That's right. And you can get it by, yeah, that'll give it to you. So, I mean, I'm using the stuff we did before. If you want to get f of u, it's going to be f of x divided by du dx. Do you all remember doing that earlier? Okay. And you're going to get this for f of u. And then, you replace x by u. Then after that, now you can go ahead and do this, because if you take a look at this, we're going to convolve these two functions. Let me put it right here. This is going to be, all right, z is equal to u, or I should say, oh, I'm sorry, it was y. It's x plus 2y.
Mm-hmm.
Not bad, guys. This should be y. That's still true. Oh, wait a second, I messed this whole thing up. I did the actual, I adapted the actual transfer function for the wrong thing. My bad. Let me go over here, since that's 2y. I don't know why. That's 2y, this is f of y. This f of y is going to be from -1 to 1, 1/2. And that means since 2y would go from -2 to +2, This is gonna have a hyphen 1/4, I'm sorry about that. So now I can say here that my z is equal to x, and this would be my f of u. It's going to be equal to x plus u. And when f of u, and I need to convolve that with f of x. So I have f of z is equal to f of x convolved with f u of u. And I'm going to go ahead and put it in terms of time. So I'm going to have f, and I'll call it z of t is equal to f of x of t convolved with f of u of t. Now, the only reason I'm doing that is I think you're more familiar with it, and I'm more familiar with looking at t's than I am x's and y's and z's. Now, this is just me personally. Now, here's how I do these things. I take a look at the two functions. If I showed f of x down here, this is f of u. F of x, 1, 2, just looks, or I'm sorry, it goes from 0 to 1. It just is this. It's 2x. And here's how I do it. You can do them any way you want. I take the function that looks like would be the hardest to flip and shift, and I don't mess with me. Now to me, it's this one, because it's got a slope. So I'm going to make that f of x of tau. I'm going to graph that there. And I'll show you mathematically what I'm doing right here. I'm going to say my f of z of t is equal to the integral. Technically, it's from minus infinity to infinity of f of x of tau times f of u of t minus tau d tau. That would be the time domain form of convolution, and for us, we'll just replace at the end of the day t by z. I don't know if you did it this way, but to me it's obvious this way. You with me, class? Okay. So I'm not going to mess and flip and shift x, and I'm just going to put up here, this is the way I always do it. Here, this is my f of x of tau. The axis is tau here, or it's the dummy variable that gets integrated out, and it looks like this. Here, it's going to have a value of 2, and this is simply 2 tau right here. Now, below there, if you look at this one, this is neat. If you take this function and flip it, it looks the same. Y'all follow me? It's a symmetric function, an even function. So when I flip it, it looks the same. Then I have to shift it. Y'all follow me, class? And if you look at this, when you flip and shift, you're going to have a span of 4. I'm going to have the front edge just come through here. So here, you're going to have a total span of 4. The upper point here is going to be t, and the lower point is going to be t minus 4. Oh, I'm sorry. I did that wrong. The upper point is going to be t plus 4. Sorry. This is going to be t plus 4, and this is going to be t. When you flip it, and then you skew it, yeah, that's right, I believe. Okay? Y'all follow me, class? When you flip and shift, you got to get these things right. And actually, this is t plus 2, pardon me. And this is t minus 2. I'm so sorry about this. The width is going to be 4, but remember, it was centered about 0 originally. So when you actually flip and shift, the leading edge will be advanced by 2. That's that t plus 2. If you look at that, when t equals 0, right, this thing shifts back and has the exact same right form. You all follow me? That's one thing you have to check on is, once you do a flip and shift, let the value t or z go to 0. Make sure it reflects that, the symmetric one, or the flip version if it's not symmetric. Okay, now when you do the integration, you're going to see several regions, right? If you think about this, this is the 0 point. So from 0 to t plus 2, if t plus 2 is going to be less than 1. Follow me on this, class? That's the first part. We can do it real quick. I'll just set it up. So the first part is going to be f of z of t is equal to the integral from 0 to t plus 2 of, and it's going to be 2 tau, and its height is 1/4, divided by 4 d tau, and that's going to be 1/2, and tau squared over 2, so it's 1/4, and it's going to be tau squared, a value from 0 plus t plus 2. So this will become t plus 2 squared, and if you want the z form of it, it would be 1/4, and it would be z plus 2 squared. And this would be for t, or I mean from z from -2, this is valid, from -2 greater than z, and it would be less than -1. You all agree with that, class? That would be the range for the validity. By the way, I think that's the answer, as I recall, for that part, right? Now, the next part is what? And I put the z value in there. If I wanted f of z of t, or whatever, once this thing moves through here, if you let t go to what? T goes to -1, now we have total overlap. Correct, class? It's going to be overlapped from t equals -1, t equals, if you think about this, the width here is 4, so it's going to be overlapped for 3 more time constants, 3 more seconds. Do you agree with that, class? So for t or z, it doesn't matter at this point. And I might as well just write z here because I'm not going to have enough time for that one. From z equals -1 to 2. Now it's going to be equal to the integral from 0 to 1 of 2/4 tau d tau. That simply is going to be, well, that's going to be 1/2, so it's going to be simply 1/4. Do you agree with that? This is one of these things, it's basically a shark fin that you pull apart. You're going to extend it for 3 seconds in the middle. Shark fins, you know, they look like a leading edge like this, and then the falling edge is like this. But that's from -1 to 2. Finally, when the thing's moving through, same time, just show you. As the thing's moving through, this is going to be t, when I did the flip and switch, is -2, and it would overlap. This is still going to have 1/4, but the overlap area is here. So now the f of z, I'll put it of z, will be equal to the integral, and here it's going to be z minus 2 to 1 of 1, really 2/4 tau d tau, and that is going to be 1/4, and it's 1 minus z minus 2, and this will be true for z greater than 2, less than 3. Yeah, that's right. And that means you get what? 1/4 times 3 minus z, or z,
I think z minus 2 is supposed to be squared.
you're right about that, that's me, you're absolutely right. And that would do it. Follow me? It's kind of a long one, so I'm spending this much time. But I did want to make one point. On this particular problem, you can't reuse Laplace transforms to do that easily. You can do it, but here's what happens. This function right here, when you convolve, or when you get, what is this function in a mathematical statement of this function? This is called a rect, isn't it? R-E-C-T of t over the width. And the width of that function is 4. So it's either, or it's called a pulse function, p of 4t, or rect of t over 4, right? You get that function, you're convolving with this. This is this function right here, 2x, right? I mean, the actual original one, 2x, if you replaced it with t, it's 2t, but then it would be times a rect function, all right? It'd be rect of t minus a half over 1, because it's centered at a half. Follow me? You'd have that same boxcar there, but it has to go from 0 to 1, so everything outside the 0 to 1 range would be zeroed out. Those transforms aren't that easy. Do you remember what the transform of a rect function is, or a pulse function? Anyone? It's called a sinc function. All right? And sinc functions, if you think about that, they don't easily go back and forth in the two domains. Those are kind of tough. Pulse functions transform to sinc functions, but sinc functions times something else, I mean, times that 1 over a plus s, and you got the sinc crazy function. It's not easy to do. I'm not going to even go there. Don't use Laplace transforms for this one. And actually, you can't, because that function has negative values for the actual horizontal axis, and you can't. Laplace transforms are only for functions that are in the positive portion of the axis. But anyway, that's what that function spent a lot of time on. Oh, one other thing. So we got a lot of. Now I did these problems. I think I put several of the solutions up there. Here's the one I want to do next. It's 3-5.3. I don't think I assigned that, did I? 3-5.2 was assigned, wasn't it? Did you all do that one? That's a commuter trying to catch a train?
Mhm.
Did you do it? Oh, you did? Anybody do it? Did you do it? That's a good problem. It's a hard problem, because you've got to state it exactly correct. But if you do that, it's not a bad problem. What I wanted to, thinking about this. I'll tell you what. I wish everybody would have done these problems, but I'm going to, for the quiz, this section and the prior section are going to be what's reflected on a quiz. Do you all follow me? What's reflected on a quiz. Now, what I did want to do, I got 15 minutes. Well, let me actually do this. Let's try. Anybody try the second problem, 3-5.2? You, besides you? Anybody? I think I want to set this one up. This is the class of problems you can expect, this type of difficulty. I mean, all of them are fair, but this problem is a little different because you have to create mathematical statements for the verb, or for the verbages. And then I've got to get to that PowerPoint because we got a little behind. I want to make sure we cover all the material. Okay, for this one, he's going to, you want to read it to me?
Yep. The commuter attempts to catch the 8 a.m. train every morning, although his arrival time at the station is a random variable that is uniformly distributed between 7:55 a.m. and 8:05 a.m. The train's departure time from the station is also a random variable that is uniformly distributed between 8 a.m. and 8:10 a.m.
And this is departure, right? Our first thing, get rid of the 8. It says at 8 o'clock, between 7:55 and 8:05, the commuter arrives. It leaves between 8 o'clock, the train leaves between 8 o'clock and 10 o'clock. I'm going to call that X, call this Y. Follow me, class? Now, what he wants is, he says he wants the difference in the arrival minus the departure. Isn't that right?
Yes.
Okay. So he's going to say he wants Z to be equal to, and you can do this problem several different ways, but it's a hard problem if you don't really focus on it. So the arrival is X and the departure is Y. The only reason I'm doing that is because you're used to X and Y symbols in Z. Now I got to tell you something. So if you think of what that is, here's the arrival. Anytime, or if he arrives at 8:05 and the train departs at 8 o'clock, he ain't gonna get it. Follow me? Maybe I should do it the other way then. I'll go depart, so I want to keep this something where positive means something. So I go departure minus arrival. Let's see if we can get that. So anytime that's positive, the departure time is after the arrival time. He catches the train. That's what I should have done, right? And if the departure time, if that's negative, basically, he doesn't catch it. That should make sense. Now, if you look at this, since I have Z is equal to Y minus X, that does not fit the form, or we can use correlation if you want, right? We can say if this is the case, then my F, and I'll use Z here. No, I want to use T because it'll be more apparent. Now that's going to be still the integral from minus infinity to infinity. And it doesn't matter which one in this case. We'll use better. Yeah, it will be F y of t times fx of, and now it's going to be t, or I mean tau, pardon, of tau, t plus tau d tau. Let me explain something here. With convolution, if that was a plus, this symbol would be negative. Because it's negative, this becomes a plus. Do y'all remember that? This is actually not convolution, it's correlation. And it's, you can't use the tables, basically, is what I'm telling you. You got to do the integration. If you take a look at this, I'll go ahead and, let's see, I left Fy alone, so I'm going to put it up here. I think you can follow me. So I'm going to have my Fy of tau here, and that just is this. This is versus tau. Has a height of 1/10. This is 10. In the other one, you don't flip or shift it, but you have to go ahead and adjust it by t. So for this one, the upper point is going to be 10 plus t, and the lower point is going to be t. If you look at this, I'm going to try to draw it right. This is going to be my fx of t plus tau. It has a height of 1/10. And oh, I'm sorry. Let's do it this way. I have to take that one there and this is gonna be 5 plus t, sorry, I put it down here, my bad. Should have left that alone. This is gonna be t minus 5. So this one's gonna come over, I'm trying to write this, to get it to the point where here, this is 5 plus tau, and this is gonna be, or t minus tau, and the height is 1/10. Let me just, so at the end of it, this is f of x. T plus tau. And at the end of the day, my f of z of t would be the integral of fy of tau times fx of t plus tau d tau. And we're going to get a bunch of different regions, but first, can everybody see why I did what I did? I just want to make sure you understand. I'm setting up the problem, but I'm using t instead of z because I think it's a little, you're more familiar with it, less confusion. If you do that, you can see there's going to be several regions. First is for t less than minus 5, there's nothing. There's no overlap. Then for t equals minus 5 to until it moves through and superimposes the plus 5, that's another range. Then from t equals greater than 5, but let's see, less than 10, I think, is going to be the other range. As this thing moves through, I might be wrong. But here's one thing I want to tell you that you check. The width of that is 10. The width of this is 10. F of z will have the width of the first plus the second or 20. It has to be. You with me? As a matter of fact, how many know that this is the old boxcar problem? If you know where the boxcar problem, and basically the integration starts, it's going to start at minus 5. It's going to have a length of 20, so it'll stop at plus 15. You all follow me on that? Remember, the width of two functions convolve is the width of the first plus the width of the second. How many remember that? From signals? No? Do you remember?
Now that you mention it, yeah.
Do you remember? All right, this is important because it makes the integration easy, that's why. Now watch. If I come down here, I'll just draw it for you. I can write the integration and do it mathematically, and you're going to see there's going to be these regions. But here's the nice thing. You get two boxcars like that, and they are boxcars. By the way, they're exactly the same in terms of their shape, dimensional. Here's what you end up doing, and you'll see this. My f of z, and I'll put of z here, of z. I know it starts at minus 5, and I know it's going to stop minus 5, and then add the 2 is 20, it's going to be at 15. It's going to have a peak dead center because they're identical boxcars. We can do the integration, but the spare time. So if I think about this, that's going to be at plus 5, and it will look like this. Basically, it's going to be symmetric like this. The peak value there, how do you get the peak?
The derivative again, what is there? You said?
Think about this, when these two boxcars overlap, right? That's going to be at the 5-second mark. When they overlap, what are you getting as total area? Well, it's this area times this area, right? Or it's 1/10 times 10 times 1/10 times 10, or, well, really, think about it though. It's actually, what I said was wrong. When you look at this, when they exactly overlap, right, you're going to get a width here of 10 and a height of 1/10 times 1/10, or 1/100th. You all follow me? Just multiply. 1/10 times 1/10 is going to be 1/100, but the width, when they exactly overlap, will be 10. The area under that curve, which is what the convolution integral gets, is going to be simply 1/10. Do you see it? That means right here, at the peak value here, it's going to be 1/10. We can do the integrations. I promise you this is it. That is f of z. And you can check and see if it makes sense. If you take this, so it's linear from here to here. So if you take width of 10, height of 1/10, right? And I know there's going to be this area too. That's exactly 1. The area under this curve is 1. It makes sense. The area under f of z is 1. And this is the shape of f of z. We can write down the mathematical form of it if need be. But what does he ask now? Now, this type of problem will throw you if you don't do these things and really know how to do them.
The probability that the commuter will catch the train.
Okay. Now, the way I've done it, that's the probability that z is positive. Do you all see? Now, listen to this part. This will help you. Because here's what people will do, and they'll spend too much time. They'll go say, well, here is the 0 part, so I'll integrate all this. Y'all follow me? You can do it that way. Mathematically, you're right. How about I take 1 minus this area? Y'all agree with that? Now, what is this area? I'm really doing my best to make sure you appreciate why I'm showing this. This little picture right here is a whole lot easier to deal with. Now think about this. Here's 1/10. It's a linear line, right? That means this point is 1/20. Following? I mean, think of it. From here to here is 10. It's linear. From here to here, it's 1/10. From here to here would be 1/20. So if you look at this, what I really want, that's 1/20. The span here is going to be a width of 5. So the area here is going to be 1/2, and then it's going to be times 1/20, right? Times 5, or really it's going to be 1/4 times 1/2 is 1/8, right? Can you follow me on this? And that means the probability the commuter catches the train, or really the integral of f of z dz from 0 to 15 will be equal to 1 minus 1/8, or 7/8. I believe that's right. Is it?
Yeah.
All right, are you with me on this? I'm going to tell you, these problems drive you out of your mind if you don't do a bunch of them, because you'll kind of, especially some of the problems, 5-3, it's just really, it's a different level. We did that last night. What's the next problem? Yes. That's the probability he catches the train. Go ahead.
Yeah, that was it. This was the last one.
Is that the last part?
There's a part, see if he gets delayed by 3 minutes
Yeah.
by a traffic jam. Find the probability the train will still be at the station.
All right, so what do you do?
You got it.
By 3 minutes?
Yeah.
Basically that you're going to catch the train, right? So now, not from 0 that he catches the train, but you're going to go to 3 and integrate from 3 up to here, right? And how would you do that? I'm just asking this. This is a stupid question. But now, instead of the probability he catches the train, remember from -5 to 5, it's got a height of 10, right? So from -5 to +3 is a span of 8, right? You know the slope of this is going to be, if you look at this thing, this basically has a slope of 1/100th, correct? If you think about it, rise over run, the rise is going to be 1/10, the run is 10, so it's a slope of 100. So you're going to have a span of 8, right? Now, for the second part, it would be the integral of f of z dz from 3 to 15, which is really going to be 1 minus, and then you got to get the area that would be not the 5, but this is going to have a width of 8, and this wouldn't be 1/20th, it would be 100th times 8 for the height. And so this area here, call it 8.2, would be equal to 8 squared over 100 and divided by 2. I don't know what that is. So it's 64 by 2 is 32 over 100. And what is that? I don't know. Can you tell me?
I got it. .32.
Is that what the answer is?
I think it's 0.68.
No, it's gotta be .32. Can't be .68.
The final answer is, but that without subtracting the 1 minus. So that's the probability. The .32 I think would be if the train wasn't there. So
What is this? Is this point, oh, I'm sorry, that is,
yeah, so then 1 minus. Sorry, I just did the 32 over 100 is .32 obviously, and then
yeah,
1
but
minus
that's
that.
just, that's
Yeah.
this area, but the probability he catches it should still be up here for the trains at the station. They have a different value for that?
0.68.
Well, it is .68, isn't this
Mhm.
.68?
Yeah.
Okay. 0.68 approximately. Okay. Can you give me 4 minutes of your time? I'm over, I'm gonna go quick, but I really need to do this. And I apologize for showing up late. I just wanna make a point. We're gonna skip the characteristic function. And we're basically done with the third chapter, but this is going to be equal, what I wanted to mention right now is going to be chapter 4. And the reason I'm doing it right now, I'm just trying to put this out there. And I'm gonna ask you please to take a look at this. Now, here's where, this is statistics, but it gets, you know, all those polls you hear about all the time and, you know, like back in the elections and stuff, oh, somebody's got a 50-point lead on somebody else or something, all that crap. The problem is their sample sizes don't reflect the proper actual relationship to the general population. It's almost impossible these days to have a legitimate poll because they use phones. Do you answer poll questions on your phones?
No.
I get them all the time. I have yet, I think this year, to answer anything other than I try to always tell them don't call. It's about the only response I have. Here's where it gets interesting. But it also is important in solid state processing, by the way. Take care of that. And finally that. And I'm gonna go quick. And I owe you time. You get the quiz early, I guess. But I want to get done. What's that? It was on. He uses this, doesn't he, Ben?
Mhm.
All right, I see some. It's coming up.
Mhm.
So my laptop connection is in.
Is that not your laptop screen? Is that the the computer? Oh.
Is it an extended?
What's that?
Is it an extended mode instead of duplicate?
Frank, you mean my laptop?
Yeah.
Display. Let's see. right, real quick. From now on, if you have, I'm trying to show you this, if you've got a whole bunch of values of resistors, this is an example, and they're plotted here, you can sample, randomly sample all those values of resistors, and you're going to get something. I mean, the true mean is just if you average them all up, but well, can't these things go down? You want the population, okay. Anyway, you sample 3 values. Well, what's the mean of the samples? This is called the sample mean. Go figure. It's the sample mean. However, if you're talking about a capital X of I, we're talking about sample, now the sampling becomes a random variable. We don't know what 3 samples we took. And then the random variable sample mean will be the true mean. What it's really showing here is even if n is a small number, if you count a small number of samples, if the way you're sampling is going to be random, so you don't know what you're grabbing, you're going to have a mean. You see how that mean has a hat over it? It means it's the statistical mean of the actual, of a sample size. But this mean will be the true mean theoretically. Now, this is not going to make a lot of sense to you, but I want to get to one point. So he's showing if you just take 3 values what the mean is. However, as you remember, he's taking 3 values and just averaging. As you take a larger number of values, he's going to show you, it becomes, as the values get larger and larger, it becomes the actual true mean. Now the question is, how precise or how close are we if we sample things, take a mean to the true mean? And this is statistical theory. It's called the variance of the sample mean. You're going to love this. So now we have something where we sample a group of things, and we have the mean of the samples. There's a true mean that has to do with the actual mean of the samples. Then there's our mean of the samples, and statistically, how does that relate? How does the mean we have relate to the true mean? And you need the variance of the statistical sample mean. Now, this gets kind of weird, but this is the way real probability works. When they do polling and all that stuff, and with VLSI processing, when they make chips, now they're going to sample every millionth chip, or maybe every 1,000th chip, and they're going to analyze it and see if in fact it's functioning right. And they'll do this hundreds of thousands of times. You won't believe how much sampling and testing goes on. They use that information to predict the outcomes of what level of confidence they have in the performance of the chips and stuff. That's why this is so great. Where I'm going to go with this is I'm going to deal with a lot of stuff that has to do both the mean and the variance of samples. And I'll tell you what else we're going to get into. We're going to get the variance of the variance, which gets more bizarre. So what we're really taking a look at is we're going to have sampling is the focus, and how confident you are with the information you extract from the samples reflects what the real information is in the populace. One thing you're going to take away from this, there's something called confidence interval. You're going to find that whenever you read polls, the one thing you need to look at is the confidence interval, and you're going to see it's so poor on almost every poll that we do in the United States. It's ridiculous. And it's just, can't believe how much disinformation is out there. Now, the groups of people that do it right, that really know how to do this, are advertisers. You know why? Because they make money by showing the method of actually getting correct information from people that make product. Have you ever been paid to do a survey? Oh, I have. They will tell you, if you do this survey, we will give you $25. A lot of times it's a gift card. Don't go for the gift card. But or they'll say you're going to be part of the drawing. You might get something. But the higher up you go in your career, you're going to find out that they want to know what you think. And one of the problems is they don't know how much of the truth you're going to tell them. But they have to start somewhere, and they will pay you, and they do a lot, they pay, they will make sure you're on their preferred call list or email list, and they'll pay you because your information is valuable to them, and they may have 100,000 or 1,000, something like that, people that represent the people that they want. And it's usually in a very specific sector, like if you're in the military and you're doing radar work. Well, your opinion is real important to them about certain things. If you're, if you're selling burgers down at the corner store, they probably don't care. They're not going to do anything. But the polling becomes very selective. But the majority of polling, from what I understand, done in this country, has a sample size that has just about no confidence as far as what group of people, the demographic they reflect. And you're going to find they try to account for that, but they don't. I don't know if you've seen the analysis on, you guys can go, I think it was the 2016 election. The polls weren't just wrong, they were grossly wrong. Then people began to think they were trying to use the polling information to skew the behavior of the population. They were trying, well, she's going to win. I think it's really funny. She's going to win, why even vote, right? Well, that was the idea, but everything in those polls was doctored wrong. Thank you for staying. I owe you something. Did you guys get anything out of this?
I really got to go over signals and system stuff.
Well, it helps